Thank you for coming. There are many amazing talks here, so I appreciate each and every one of you who chose to come here. Today we're going to talk about generators, coroutines, and a few more interesting syntactic sugars. My name is Adi. You can find me on Twitter or my blog. And I want to talk about iterations. So say we have a vector that we want to iterate over. We can write a function, a regular function, call it vectorate. And basically, we iterate over the sequence of the vector, and then we print out the elements. So we can see that this one function or subroutine, the concept of subroutine actually goes back to the late 40s, so it's not very modern. And we can see that we have one function vector that does two things, which also already violates one of the principles of good software design. It both iterates over a sequence and performs some operation. And the question is, let's say we want to do some other operation. Maybe we want to sum the elements. Maybe we want to sum them and print them. Or maybe we want to do some operation which whoever wrote this function wasn't aware of. So in that case, we would actually need to write a new function which does these extra operations. We can think of another example. Let's say we want to draw a line on some image or in a device. So again, we can copy, go to Stack Overflow or any computer graphics book, and we generally see code that looks something like this. This is just a partial Bresenham algorithm for drawing a line. And the thing, well, I'm not going to go into the logic, but you can see that basically it also does these two things. It iterates over some values, and it calls this function putPixel to actually draw the line. So again, we're iterating and performing some operation. Now, by calling this function putPixel, we're actually making some very significant assumptions about this function. First of all, we're actually assuming that it exists and that we can actually, the compiler can find it and the linker will link it, right? So we're assuming that it's available. We're assuming we're calling it correctly with the correct signature. We're assuming that it actually does what we hope it will do, which is draw the pixel. And another implicit assumption that we're making here is that it will actually return the control to our function, because this function is actually in the middle of computation, right? So we're seeing a mixture of these two things, which are iteration and operation, mixed inside as two concerns that are mixed inside a single function. So we can summarize this, or at least the features that we see here is that subroutines are both eager and closed. What does that mean? Eager, it means that they operate on the whole sequence, which is passed in as an argument, and closed in the sense that we have to predetermine what operations these functions apply to the elements of our sequence, right? So some of you might jump up and say, yeah, you can make putPixel a callback. And a callback is a very common way to overcome some of these limitations. But you know, C++ actually has many different mechanisms for using callbacks. We can use function pointers, we can use lambdas, callable templates, or we can use concepts. There are many ancient and advanced modern ways of producing these callables. However, regardless of the mechanism you're using, you still have several problematic issues related to callbacks. The first one might be called inversion of control. Essentially, we're letting library code call external code that is not necessarily trustworthy or valid or correct, and we're still in the middle of computation. The second thing is called, you can call it callback hell, is really when the flow of your algorithm, the flow of your program is skipping between decoupled parts of your code. So trying to reason about or debug or understand or maintain your code becomes extremely difficult when the logic is all over the place. Sometimes it's not even in the same file. And even still, the code is still eager. So we're still calling this external function on the whole sequence and not calling it directly. So the functions are still expect to get to receive the full sequence. So, you know, the question is, if only there was a way to somehow flip these iterating functions. I kind of think about it like inside out, so that we can somehow iterate without pre-committing to a predetermined operation, so that we can decouple the operations we want to do on the elements from the iteration itself. And the answer is also not very modern. It comes from originally, I think, from Alexander Stepanov. It became part of the C++. The C++ standard library has iterators since 1998. And two of the interesting concepts related to iterators are iterator objects and iterator adapters. These are usually standalone types. And frequently, they're not very tightly coupled to an actual sequence. That means they're not, sometimes there isn't even an actual sequence underneath. We can see some examples from the C++ standard. STD iStream iterator is a single pass iterator that reads successive objects from our stream. And it calls the operator the input streaming operator. And the actual read operation is performed when the iterator is incremented, right? Not when it is the reference. Now, STD reverse iterator is an iterator adapter, and it just reverses the direction of a given iterator. So plus plus actually would actually call minus minus, for example. And we have in C++ 17, we got recursive directory iterator, which iterates over directory elements of a folder in a recursive manner. So it basically iterates over the whole subtree hierarchy. And I bring this example because here we don't actually have some explicit sequence in the memory of our program. So there is no sequence. The sequence we're iterating over is actually the file system. It's external to our program. But still, this is a very convenient type, and provides us some very nice abstraction for iteration. Now, another option is to write our own user-defined iterators. And I chose this. I work a lot with OpenCV. I do a lot of computer vision and image processing. And OpenCV has this iterator class called line iterator. Basically, it creates iterator for line connecting point 1 to point 2, and gives us the ability to skip from one to iterate across along pixels along this line. So that, and the API is actually very typical for iterator types. We can see that, well, it has, I'm going to go over the methods in a minute, but basically the important thing is there is no explicit sequence. The iterator object is actually calculating the line elements one by one as it's dereferenced. Sorry, as it's incremented. So there is no underlying sequence. It's what's called lazy, because it's only calculating the next element whenever there's actually a request to get it. It's on demand. And we can see that it has the dereference operator, which gives us a pointer to the current pixel in the image. The constructor takes the image, the 2 points, and some connectivity, which defines which of the line algorithms it's going to choose. The increment operator allows us to go up to the next pixel. Now, and it also has a bunch of public members. Okay. However, and the way you use it, it's actually very simple. I just copied an example from the documentation. We can create the line iterator. Let's say we want to copy the values, the color values of all the pixels inside this, along this line into some vector. And so we can run a for loop, and our counter I goes from 0 to it.count, again, that global member count, where we can increment both the iterator and the count. And then we need to cast the pointer type, because the type of the pixel is not always known at compile time. So there's this ugly cast over there. I don't really want to go into too much criticism over OpenCV line iterator, but that's one of the ugly things about it. And basically, objects that lazily generate values are called generators. Okay, so this is an important term. We're going to see more of it a little bit later. Now, iterators themselves are also an imperfect abstraction. Okay, they're maybe better than what we saw before, but they still have several issues that we might want to see how they affect our code. We saw the global members. Hopefully, we could that's fixable by using some access members, and also the casting. We could have made it a template or derived the template from it, but the more severe concerns that I want to talk about are actually relevant for all of the iterator types, and those are the ones I want to talk about in this narrative. The first one, I'm not sure, it probably has a more formal name. I generally call it the awkward coupling problem. And it comes from the question, when do we stop incrementing? Because we have these iterator objects, and we somehow need to decide how long we're going to, is it allowed to increment our iterator types? So for CV line iterator, we saw that it has this member called count, and we have to check some external counter against this number, and we shouldn't count beyond this value. For iStream iterator, there is a default constructed something called the end of stream iterator, which becomes whenever an iStream iterator reaches the end, it suddenly becomes equal to this global universal iStream iterator from the standard library. The reverse iterator must be compared to the underlying sequences end iterator. And the recursive director iterator, basically it's checked by comparing it to calling the free function std_end on the iterator itself. So maybe this is not the only way to do it, that's one way to do it, right? So we're seeing that there are actually many different methodologies or policies for identifying when we want to stop iterating, or when we have to stop iterating. Now, to make matters worse, especially in cases where we're comparing our iterator type to another object, is that the user, let's say we want to do some kind of call an STL function that expects a begin and end iterator. And let's say we have multiple such sequences that we're iterating over. If we pass the beginning iterator of one sequence and the end iterator of another sequence, the types still match if the underlying are the same types are the same types, but now we have undefined behavior. We're actually requiring the user to make sure that they pass the begin and end iterators of exactly the same underlying sequence, otherwise not other people's problems. And that's an abstraction problem that can cause undefined behavior. So in the best case, your code will crash. In the worst case, it won't. And nobody knows when and if it's correct. Any questions? Didn't know? Oh, okay. Right. So since the upcoming standard, C++20, we're getting ranges. And ranges are amazing, an amazing addition to the library. And they're kind of an abstraction layer, a more general concept over iterators. And they're basically the answer to the awkward coupling problem, because they by creating a range, you're coupling this begin and end iterator into a single object. And also you can encapsulate not just a begin and end, but a begin iterator and some size or count initially, or some other stopping conditions or sentinels. There are different ways to create a range, but once we have a range, the range is actually encapsulates all this information itself, and there is no problem where we might mix iterator types. And it also makes working with the STL much more powerful. It allows us to do composition of multiple operations. We can create pipelines, transform values. It's actually a very, very powerful library, which I'm not going to talk about, because iterators have another problem, another abstraction problem. And that's the problem of distributed logic. And ranges don't help us solve this problem. Actually, what I'm going to talk about in coroutines, we're actually going to think about how ranges are built, how we can create our own ranges, which are iterable types. Okay, so every generator we're going to create is actually a range, and these, from a user point of view, a range is almost, is in terms of usability, it's very often indistinguishable from anything else we're going to see here. So I might be using these terms alternatively. So the problems of distributed logic is kind of a cousin of the callback hell. Because if we look at the implementation of this line iterator, which we see on the top, this is just the same code I showed before, and a few of the method implementations, we can see that the dereference operator is trivial. It just returns some kind of the value of this member, the pointer, and the increment operator does some kind of computation. A very simple, very short computation. There are no loops here because, remember, the iteration is abstracted, is externalized to the user. And the other part of the logic, basically what sets up these values to do the right thing, happens in the constructor, which isn't shown here because it's actually longer than the screen. Okay, so it's a whole bunch of code, does a lot of pre-computation to fill in all of these elements, and then we can call the increment operator. Now this has two problems. The first one is the fact that now if we need to write our own iterator type, if we're writing our own algorithm, we now have to start thinking about, okay, let's debug the code that happens here. And how does this relate to the constructor, which may be written in another part of the file? Maybe we also have a post-increment operator. Maybe we have additional operators. And suddenly we have to keep all of this logic, distributed logic, in our head and try to track it across the implementation of the iterator type. The second problem is centralized state, where you can see all of the members are actually stored as all of the variables that are needed in here are actually stored as members of the object. And this doesn't take any note. We're kind of leaving things like constness and scoping rules and all kind of, not all methods actually need to access all of these members. So it might also affect the object size and other such considerations. So we have distributed logic and centralized state. Some of them are not, and all of them are mutable by all of the methods at least. Well, if they're public, then by anyone, but let's assume they're not public. So if we want to compare this distributed logic to what we saw before with functions, I can just copy this logic into a single function. Let's say this is it's not a function from OpenCV. I just wrote it slideware, basically a function called process line. It takes the same arguments as the constructor, sets up all of these members as local variables, calls the same logic as the constructor, and then we have this internal loop. So this process line is actually very similar to the drawLine method that we saw before, and this has the centralized logic, but again, the problem that we saw before, it's both eager and closed. And by working with iterator types, we have distributed logic, but it's lazy and open. So we kind of have to make, it seems like we have to make a trade-off between iterability and laziness and openness. And we're sort of trying to figure out whether we can have both, the best of both worlds. Is there a way to write easy code that we can reason about and write our code in a serial manner that we can maintain and debug while still abstracting away the iteration? And basically, this is where coroutines come from. And the simplest definition of a coroutine is basically a coroutine is a function that can suspend execution and be resumed later. Okay? So it allows suspending and resuming execution at certain locations and preserves its local state so that when we re-enter it, we can re-enter it more than once and continue wherever we left off. And in contrast to threads, it's not, it's kind of a cooperative yielding, basically. So it's non-preemptive. So it's not like a thread which is interrupted or scheduled by the operating system or the kernel or maybe the CPU. It's actually the code itself decides when it yields its control flow back to the caller, and the caller can decide to resume it. So in a sense, the coroutines I'm going to be speaking about are only synchronous coroutine. Okay, so again, this is not a talk about all of coroutines. Coroutines is a huge subject. The concept goes back to 1959 when the term was first coined. And in fact, Boost has already had several coroutine libraries since at least 2009. So this is not a new concept. And I've seen coroutine libraries from C, especially for things like generators, like we're going to talk about, that are essentially before the year 2000. So this is not, it's not a new concept, and it's not a new solution in the sense that people have known and have worked with coroutines before. And if we think about the function that can suspend execution in mid-operation, return some value to the caller, and then whenever the caller requests can resume execution, this is very similar to what we were trying to do. Basically, if we look at the process line function that we just wrote before, remember, here on the left, the nice thing about it is that we have this centralized logic, very serial code, the serial algorithmic code. However, whenever we get to do something with the pointer, what we can do basically is, this is where we want to stop and return the value of this pointer, just like the CV line iterator did with the dereference operator. We can say, okay, let's pause here. This is the current value that we're talking about. Take it, do whatever you want. If you want the next one, just call me again, and I'll resume this loop. Okay? So, and we're going to see how this works. Now, the interesting thing is that operating systems and most modern CPU architectures, and even not so modern ones, already have support for fibers. That's kind of a context switching of such coroutines. And that's what the Boost Coroutine 2 library uses. But we're not going to talk about that. Although you can use the Boost to do that, we're not going to talk about it because there's a new kid on the block, and that's C++20 coroutines. So our answer to the distributed logic problem, as we saw, is a coroutine. And so you might say, okay, but what is a coroutine? And the answer is a coroutine is a function if any of the following is true. Basically, if it uses the co-await keyword, a keyword or one of them, the co-await operator, or the co-yield and co-return keywords. And that's it. And the interesting thing is, notice that all of these requirements are only on the implementation side. So there's actually no way to distinguish a regular function from its prototype from a coroutine. But however, you know, a coroutine must return a certain type which satisfies certain requirements by the compiler, so the compiler can generate the coroutine code. However, we can also have a function that returns the whatever a coroutine calls, so, and that wouldn't be a coroutine itself. So a coroutine is actually an implementation detail for creating something like iterables or ranges. It's not something you can see by just examining a header file or forward declarations or functions. Now, there is a proposal. It's P148.5R0, at least at now, which suggests adding another keyword async to the end of the definition. But again, that's not at the declaration. And it makes it a context-sensitive keyword. I'm not going to go into that. You'll note the ugly co-await, co-yield, co-return. That's a whole other discussion about style, but that was what the committee chose, so that's what we're going to live with. And I'm only going to be talking about the co-yield keywords. So I want to make this clear. I'm only touching a very narrow part of what coroutines can do. And my goal here is to talk, it's a kind of a motivational user and usage point of view, and I'm not going to go too deep into how things are actually working underneath and about the magic that the compiler is doing to get us these amazing features. So there's a ton to see about coroutines. There are excellent videos about it, and we're only going to touch, but I think it's enough. So now let's see some code. Okay, so we have a function. I have a question, not a trick question. What does Zoro return? 42, yeah. And the return type is? Int. Is it a coroutine? No. Why?
There's no special keyword.
Exactly. Right? Easy. Okay, so now we have this function, coro. It uses the keyword co-yield. What does it return?
Coroutine?
Not 42. What's the return type?
Coroutine object.
Yes, it's a coroutine, right? So how do we use it? Well, there are actually several ways to use it. The first one, this is maybe the more explicit one. We can save gen is the object returned by coro. It's a range. I'm going to call it a range because it is a sort of range. It supports the range API. And we can get an iterator to the begin and decrement and dereference it to get the actual value. Or we can just, for example, print it that way. And one of the most common ways to do it is just use a range for loop, like at the bottom. And I think this is pretty amazing because we have this very linear code here. It's extremely linear. It's single line, right? But it's linear code that created by the compiler gives us this whole way to providing all of the API that we saw before that all iterator types must support. So if we thought that C++ 11 lambdas brought us some very impressive syntactic sugar in code generation by the compiler, we're going to see that coroutines go like a whole atmosphere above that. Now, of course, nobody said that there must be that coroutines must provide an actual sequence, and since they're lazy anyway, there's no reason to not use infinite ranges. So in this case, I have this function called a coroutine called iota, and it just loops infinitely and returns incrementally the values of n. And for example, we can use copy n. I'm creating the coroutine here with the initial value 42. We're calling begin because again I'm using the standard copy n, which expects a begin and end iterator. Then I can say copy n requires an iterator and the number of the number of increments or in values we want to expect, and then we're just printing it to the output stream. So I think this is pretty awesome. Note that because it's unsigned, it's not going to go all the way to an infinite number of values. It's actually going to wrap around, but it's not undefined behavior. Okay, so actually I lied. That's not that code that I showed you is not valid C++20 code. There are actually several problems with the code. It does run. By the way, all the examples I'm showing you here run on Visual Studio. But it's non-standard and non-conforming. But it might give us a peek into the future, and it gives us a sense of it's much easier to explain. So I'm going to stick with it. And the first thing is that there is no such thing as the auto return type or concept return type on coroutines. So the fact that I wrote auto coro and asked you what the return type is, that shouldn't compile in a pedantic mode, in a totally conforming compiler. Because what Microsoft Visual Studio with the coroutine extension does, it actually infers a type called std experimental generator t whenever I wrote auto. And it can infer that because I used a co-yield to yield an integer. So in that case, it would be a generator of int. Which is very convenient. It makes for very easy to read slides and no need to have a lot of using namespaces. But as C++20 stands, that's not valid C++, and we have to explicitly state the type. The more serious problem here is that there is no such type as std experimental generator. There is no standard generator. In fact, there is no standard library type that does anything with coroutine. There is no support There is no library support for coroutines in C++20, and that's unfortunate. C++20 brings us very, very powerful low-level mechanisms that explain how linear serial code using these keywords is transformed into something that generates generators and other interesting types, but it does, and it tells the library writers what the APIs of these types should look like, but it doesn't actually come with anything like a generator. So again, STD experimental generator is actually an extension for Microsoft Visual Studio. If you want to use it on other platforms, then Louis Baker has a library called CPP Coro, which is incredible, and you should definitely just go and read the README. It's super readable and it's mind-blowing. The code, the samples there are really amazing and easy to read, so I definitely recommend checking it out. So for brevity, I will continue using the auto keyword, but remember that we're kind of in a joint illusion that that's actually the way you write it. So let's see some more examples. A few years ago, I was working on doing some image processing algorithm, and I needed to do some processing on a neighborhood around a certain pixel where until I reached the nearest neighbor. And I decided to write the algorithm. I called it Spiral, which allows me to take a single pixel and just iterate spiral all the way until I reach the nearest pixel that has some interesting property. And the code for this coroutine is on the top. You can see auto spiral. This code works. This code generated this graphic. And I'm initializing some variables x and y to 0. And the first thing I do, I'm actually co-yielding the point x and y. So basically, it will be the origin 0, 0. And that's the first value, and it's indeed the center of the pixel. And then whenever the user decides to return and resume the iterator, there's some computation. I'm not actually going to explain how the computation works, because I think this is probably the simplest way to show it. If it was spread across maybe a constructor and different operators, it would be even more difficult to understand the logic. So there is some logic here. It's actually very simple. You can take your time later. The slide will be online. And this function generates infinite and infinite, basically it spirals to infinity. It doesn't take into account the boundaries of the image or anything like that. It just gives us relative pixel values to the center, to the origin. Now to generate these pretty colors, I said, okay, so let's create another generator which, well, cycles through colors, right? And cycling through colors is actually easier to do in a color space called hue saturation value than in RGB space. So I'm using OpenCV to create, I have two 1 pixel images. One is going to be RGB, the other one is going to be HSV. And I'm just converting from HSV to RGB because our display only knows how to display RGB colors. And then I'm converting it to RGB, yielding the RGB pixel values, which are a triplet of 3 numbers, and then only incrementing the HSV, which is it's a cyclic channel. Again, the details are not really important, but you can see that both of these coroutines are actually infinite loops. Especially this one. This one is not even going to have any wraparound issues because it's explicitly wrapping around at 255 because that's the way the hue channel works. It's a circular kind of a cyclic channel. So what we need to do now and to draw is we sort of need to look at these. Sorry. Oh, oops. Wait. So we have one generator creating positional values, and the other iterator is giving us colors. And we want to draw these values onto an image in tandem, basically incrementing both of them in lockstep, right? And how do we do that? Maybe you saw the slide. We're going to zip them together, right? So we create a new coroutine, which is called zip. And this one is actually a template. Yes, coroutines can be templates as well. What does zip do? It takes two generators, takes the begin iterators of both of them, and then simply iterates, incrementing them one by one and co-yielding a pair of the dereferenced values. So this make pair here is going to return, the first one is the dereferenced value, basically the position of our pixel, and the second one is going to be the current color. And actually, the ranges library has a much more powerful zip view implementation, which can be, this is a very naive implementation, but I think it's for me, it's actually very easy to figure out and understand the logic. There is no extraneous information, and the syntax is relatively obvious. And the way we combine them is basically in a range for loop. As we can see on the bottom, we have a for loop with I'm using a structured binding for the position and the color. And on the right of the column, we can see that we're calling zip with the spiral and the hue cycle generator. And we're basically getting a position and a color. The point we're going to draw on, again, remember that the spiral only is based only around 0, so we're going to shift it to the actual pixel that we want to draw. And some conditions of checking when the spiral is outside of the image and when to stop. And then we're setting the colors. So actually the difference in the animations between this one and this one is that for this one, I think I used the value of 10. So the changing of the hue is actually faster. So let's see another example. Let's say we have a binary tree, and we'd like to iterate over its node. Now, we might write something like this. You know, we all when we were learning about data structures, the first thing you learn about binary trees is that there are three ways to, at least three ways, well, with names that we can iterate over them. We have in order, pre-order, and post-order. And basically, what they do is they decide whether we're going to print the left child first, then the root and the right. And pre-order is the root, left and right, and post-order would be the left, right, and root. And the way we implement them is with recursion. So we have a tree node, which has some members of the actual value. And we can create three methods, which are coroutines. Okay? And let's say I'm looking at in order. And in order checks whether we have a left child. If we have a left child, we're going to iterate over all of the values of I'm going to recursively call in order over the child, the left child, and iterate over all the values from that left side, co-yielding them externally. And then co-yield the actual value of the node, and then again on the right side. And pre-order is basically the same type of code, only with a different, with a pre-order, and post-order would be the same. And we can create another function called order, which takes the type of order we want to provide, and then use, let's say, a switch to return the actual generator of the method. So what we're seeing here, we're seeing three methods which are coroutines, and actually order is returning the return type of a coroutine, but it's not itself a coroutine, because it's just a regular method. Does that make sense? Yeah? And the way we use it, basically, we can just call the order with the in order, and it would print out the values. But there's a nice cool thing in CPP Coro, the library from Louis Baker. He has something called a recursive generator. And it's very similar to the generator we saw before, except that it's designed to be more efficient in yielding elements of a nested sequence. Because in addition to being able to co-yield the value of type T, you can also co-yield the value of the recursive iterator itself. And in that case, all the elements of the yielded generator are yielded as elements of the current generator. And then the code of, let's say, in order looks like this. If left, co-yield left in order, co-yield val. If right, co-yield right. I think this is probably the most succinct way you could write such code. This is totally transparent. How, like, if you go and read, I don't know, introduction to algorithms and reading about pre-order and post-order, this is probably even shorter than their pseudocode. And I think this is beautiful. This is really super awesome. Can't get much simpler than this. Yes?
I was wondering, with this implementation, now you have exposed in the interface that the generator is recursive. Is it possible to hide that? Because it's the recursion itself is sort of an implementation detail, I guess. From the user's perspective, you just want to visit the nodes in the desired order.
I'm not sure I understand the question.
I was just wondering about the exposing the recursiveness in the type, because you say that the return type is recursive.
Well, actually here I told you I'm cheating. Well, actually I'm not. Valgen is STD experimental generator, right? So I'm explicitly stating that this is a generator.
Yeah.
And here I'm explicitly saying it's another type. It's another type.
Yeah, but it's a recursive, so you're exposing the recursion. That's what I'm...
Well, it's the name of the type. I'm just using the name of the type.
I was just wondering if it was possible to not expose the recursiveness because that is an implementation detail. Never mind.
Without type erasure? No, probably not.
Well, the recursive, of course, is just in the name of the type, right? The fact that the function is recursive is an implementation detail, but I think, maybe he could have, you might name this type as self-yielding generator or something along those lines, right? So I think we'll touch a little bit about that later if we have time, okay? Okay, so one of the, coroutines are rather new, and they're not perfect yet. They haven't gone into they'll be in the language, and they still have a few more months until 2020. So I'm going to talk a little bit about pitfalls of using coroutines. And the first one is called dangling references. So I think coroutines are super cool, but let's look at this innocuous looking code it's from a blog post. I took this one from Arthur O'Dwyer's blog post, but it's been discussed a lot on the C++ Slack, and the problem of dangling references they go way deeper than this one. This code looks pretty much harmless. Basically, we have a function called explode. It takes a string and returns a generator, and then it just iterates of yielding all of the values of the string. And externally, we take all the values and just print them out. And the thing is that this explodes. This doesn't work because we have a problem that we can't actually see in the code. So the problem is transparent. Similar to?
This is similar to the problem of in a range-based for loop iterating over a sub-object of a temporary.
Yes, exactly. I'll show that in a minute. I'll explain. Basically, we're passing a string literal here, which creates a temporary std string, which is passed to the constructor of explode. However, this temporary string actually, remember that the generator itself doesn't actually start running until begin is called, and by that time this temporary doesn't exist. So, and actually the answer is not specific to coroutines. I took this today, an hour ago from CPP reference. If you go to range for to the regular page about range for loops, and range for loops get basically there's a code generation by the compiler into this type of statement. And there is a special note there saying temporary range expression. If range expression returns a temporary, its lifetime is extended until the end of the loop. So this is what __ range is. It extends the lifetime of the temporary, as indicated by binding to the forwarding reference __ range. But beware that the lifetime of any temporary within range expression is not extended. So this is the general problem, which becomes significantly worse with coroutines. And this is, in this blog post, you can see this is like, it's called the boring example, okay? This is like the most basic example, and there are many, many other examples where coroutines can have dangling references. I've actually hit one just last week where, because generally the tip is take coroutine arguments by value. So don't use references unless you are certain that whatever you're passing by reference is not temporary and will outlive the coroutine itself, okay? However, I noticed that even when you're passing by value, let's say I have a variable that I'm passing to a coroutine, that'll be fine. But if I'm, to a lambda coroutine, if I'm passing it as an argument by value, it works fine. If I'm capturing it in a copy capture, I get a dangling reference, okay? So there are still many pitfalls and many corners, because the temporaries are created only later, and this is a very serious trap. So try to keep all of the objects you're passing, either pass them by copy or make sure they outlive the coroutine. Yeah. Oh, and by the way, one of the ways to get over this is something that we have since C++20, which is in its statement for loops. So we can see the example on the bottom. Again, this is not specific to coroutines. So this coroutines only somehow make it a little bit more dangerous because it's hiding what is actually happening. And things happen beyond the point where how much time do we have?
15 minutes.
Oh, 15 minutes, okay. So hopefully we get to the initial stage. Right, so another problem is, I don't know if it has a better name, I just call it decapitation. And it has to do with the fact that coroutines don't actually start execution until you call begin. So when a coroutine returns an object of some generator type, that generator type is kind of in a state where it hasn't begun execution yet. It's initially suspended. And we have to be very, very careful what we're actually going to do with this particular object. Because let's say we want to create a generator and indicate that it's empty, maybe indicate the creation error by creating an empty iterator. So the calling function is going to check if this generator is empty and maybe then try to create a different generator. However, by the fact that we were checking that begin and end are equal, we already called begin and we began the execution. And now if we dereference the iterator, we already have a value. So in the case where the iterator isn't empty and we want to pass it on, let's say it's a factory function, the user outside our function is actually going to call begin again and dereference it, and in most cases it will just it will skip the first value. It will decapitate the sequence by not seeing the first value, because, yes?
I'm just smiling because you keep saying decapitation and execution in the same.
Perfect. Yeah. So we have execution by the decapitation. Well, this is decapitation by execution. Yeah, not the other way around. So remember, be very careful when you're handling initially suspended coroutines, especially if we have multiple layers of functions that are like factory functions that are generating them. I think about them, it's a little bit like moved from object, where once you moved the object, you have something that you have to be extremely careful to limit what the operations that you're performing on it. And of course, generators, you have to move them and you should not copy them. I will make a caveat that since we don't actually have a standard coroutine support library, you could write generator types that have idempotent begin functions. So hypothetically, some types could have that, and then you might be able to get around this. I haven't seen this in any of the implementations. So again, don't count on it. And so just be careful when passing them around. Right. So as I said, coroutines are not perfect. They're very new. And we saw examples of coroutines that are templates. We saw examples of coroutines that are methods. We saw examples of coroutines that are actually lambdas. However, they cannot have auto-return types or concepts. They can't be const expr at the moment. You can't make constructors coroutine, destructors, or actually the main function, although I don't even know what that would mean, but I'm sure somebody will find a use case. But again, if you find a use case, then, and don't complain, 10 minutes, okay? I do suspect that some of these limitations will be removed, maybe const expr, I don't know. Because just like lambdas became incrementally more and more powerful from 11 to 14 to 17 to 20, we'll probably see that kind of progression. And of course, I'm super hopeful that we will be at one point getting a standard support library. There is a problem of quality of implementation of libraries. So for example, the Microsoft version of generator doesn't support reference type of T, but CPP Core does. You could get around it with stdref, but still, it's not exactly the same code. And it's not something you can complain about because there is no definition of a library. So everyone just does whatever they think they deem possible or whatever their experiments bring them to do. Another problem is that I didn't mention this at the beginning because it's kind of confusing. It's the fact that a coroutine must save its internal state somewhere. And this is basically, it's called the coroutine stack frame because the stack frame is external to the calling code stack frame. And in general, this is allocated on the heap. However, especially in the case of synchronous coroutines generators, it's very often that there is a compiler optimization that actually brings the coroutine stack frame back to the user stack frame. But again, and that's where it gets confusing because there are stackful coroutines, which is what I just mentioned, although they may be allocated on the heap. And sorry, stackless coroutines, and then you have stackful coroutines, which are the ones using the CPU support for fibers. So there's a lot of confusing concepts here, and the compiler optimization levels vary significantly between different implementations. So I think although a lot of the coroutine proposal came from Microsoft, the compiler was mostly working on proving that this is doable and does the right thing. Their library, at least at the beginning, was significantly, sorry, not the library, the compiler did a significantly worse job than the Clang version. So, but I do believe that these discrepancies will decrease and we will see code generate, yes?
I'm curious what's the efficiency story. So it looks like you can't escape any direction in the function call. What's the efficiency of it?
You mean like as opposed to inlining?
There's an indirection there. It seems from the examples there's an indirect call to a function.
I think it would be exactly like the regular ranges or any iterator object. It should be.
Could you go to your slide with the 3 iterator?
This one?
Next. Next.
The tree.
The tree or the 3? This one?
Yeah.
Yeah,
So
okay.
you have auto order and it takes an order at runtime and then returns one of 3 possible coroutines. So it looks like an indirect call is going to be there. You can't escape it.
An indirect call call to whom?
To the iteration routines in the coroutine.
You mean in this function? Yes. This is just a constructor call here.
Yes, you make the decision at runtime on which coroutine you're going to return.
Yes. And then you're eliding it out.
That has polymorphism written all over it. There's
No, why? It's the same type.
Yeah, but they're going to do different things. And they do different things because there's an indirect call. I don't think you can. Did you measure the speed of this?
I didn't look at the compiled code because I only tried this on one compiler and I didn't have time to actually go into checking. But this is actually the point I was making. The last point I was trying to make here is that there are a lot of quality of implementation issues. So I didn't even want to try to go into that yet, because we will see better and better optimizations and compiler elisions of all this extraneous code. So it's certainly a valid concern, and I wouldn't go running and using coroutines blindly in production code before testing. So always measure, measure, measure. Where did I hear that today? Yeah. Right. So a little bit about resources, and then I'll take some questions. There is a massive list of coroutine resources with videos, articles, proposals by Matt PD. He's a very proficient archivist. CPP reference has a nice page about coroutines. The coroutine Slack channel on the C++ Slack is very, very active, and you can basically talk to anyone who's interested in coroutines. The people who are writing the proposals, the people who are writing the compilers, they're all there. An extended version of this talk will be published as a blog post on my blog, probably in a few weeks, maybe, I don't know, before CPPCon or after CPPCon. Yeah, and that's it. So I'll take some questions. Okay. Yes.